What's up YouTube, my name is Ali and welcome back to another video in our Intro to Embedded series. This is the second video, it's video number 1. Video number 0 was setting up the environment, so not really any programming or embedded, but just installing our compiler and our libc. So today we're going to be having a look at GPIO on embedded. So this is general purpose input and output, exactly what it sounds like. On the AVR, or at least this one, there are 4 GPIO ports. We've got port A, B, C and D. These are 8 bits or 8 pins on each port that allow us to interact with the world. And some of these pins have special uses as well as general purpose uses. So the first thing we're going to do today is have a look at the datasheet. So this particular device that we're going to be using is a Atmega 644 or 644p. It's clocked at 12 megahertz and runs at 3.3 volts. So the first place we're going to look is at the table of contents. So we have here I/O ports. This is where we're going to go, and this is going to tell us a little bit about our GPIO. So if we have a look at the diagram here, we basically have a few diodes to prevent undervoltage and overvoltage, a capacitor for output stability, and then we have here a pull-up resistor, RPU. This allows us to set whether we want the input to be, or if it's an input, we can set it to be a pull-up so that it's not floating. And that's control over here. So if we scroll down a bit more, we can see there's a section ports as general digital I/O, and this contains a bit more of a complicated diagram, but it's essentially just telling you the logic behind it. So we can see for the same thing, we've got the pull-up resistor, and then we have the logic to control it. And then, so this is the output logic here, and this is the input logic, and then we have the pull-up control logic. So if we go down to configuring the pin, we find out that each port consists of 3 registers: the data direction register, the port register, which is used for output, and the pin register, which is used for input. The data direction bits are accessed at the data direction register number N, or X in this case. Same with the port and pin. And if we were to look at the register summary at the very end, we find the address of these. We'll have a look at that in a minute. So next thing we see is the DDXN, or data direction register N, bit in the data direction register selects the direction of this pin. If data direction is written at logic 1, pin N is configured as an output pin. If it's written at logic 0, it's configured as an input pin. So we've got 4 ports here, and these are going to be, the registers behind them are going to be DDR ABCD, port ABCD, and pin ABCD. The X here just represents the individual pins in each port, and we don't need to worry about that just yet. If we go back to our code, let's say we wanted to set port A as all outputs. Looking at our datasheet, we can see that to configure as an output, we need to write a logic 1 to the data direction register. So if we were to do data direction register A equals 1 shifted 0, this would say that the data direction register A, we want to set pin 0 to output. Now what you'll notice is that data direction register A isn't defined. So we know that this is going to be memory mapped I/O, because if we scroll down to the bottom and have a look at the register summary, we can see that these all have addresses, and they actually start at hex 20. This is because the internal registers of the CPU are actually memory mapped as well, and there's 32 of those. The next thing we see is that the first lot of memory mapped I/O is the GPIO, and we can see that pin A is at address 20, DDR A is at address 21, and port A is at address 22. So if we wanted to access this memory directly, we could do something like, so DDR A was 21, we want to make it a 8-bit or 1 byte pointer to 1 byte, so unsigned char, and that's made this into a pointer. And if we were to then dereference that, we can now access that bit of memory, or that control register. And then if we assign it, this works perfectly well. And that's all well and good. And it's exactly basically saying DDRA set pin DDA0. But it's a bit hard to read, so what we normally do is we would include a file, include avr/io.h. Now, at the moment, this won't do much because, well, it does do much because I've got it configured. But normally, you need to define what your core is, or processor. So we are going to define avr. If we have a look in here, we can see exactly the format. So this is the kind of thing that it's looking for. So if we find our 644p, we can copy that, and that is telling this IO header, give me all of the registers for this piece of hardware. So now, if we go back to our DDRA here, this works. And this is because this is just defined as a macro, and it will evaluate to exactly the same as this. So now that we've configured our data direction register to be an output, let's go back and see how to set the output. The next part in the datasheet is if port bit N is written logic 1 when the pin is configured as an input, the pull-up resistor is activated. We're using it as an output, so that's not necessary. Sorry. To switch the pull-up resistor off, port bit N has to be written logic 0. That's just to turn the pull-up off. If the port is written logic 1 when the pin is configured as an output, which we are, then the port is driven high. If port is written logic 0, then the pin is driven low. So we want to set that pin as an output pin. So we're going to do port A equals 1 shifted 0. And that's again saying set the 0th bit in port A. And we can now actually run this. So if we compile it, this is just saying I've already defined it, it doesn't matter. We can then set our bootloader, and it doesn't really do much, at least not visibly. That's because our pin A0 over here isn't really connected to anything, but we do have a little LED on this board, and that's connected to pin, I believe it is B7. So what we're going to do is we're going to modify our code, and we're going to make this port B, DDRB, and we are going to set it to pin 7. And if we compile this again and flash this, we can see that now our LED is on. And just to show you that I haven't just messed up the bootloader, if I try and flash it again, it won't work this time, but the LED is still on. So what can we do with that? Well, there's lots of things we can do.